Hello and welcome to this webinar from Taylor Hobson. My name is Mike Mills and I'm the Chief Metrologist at Taylor Hobson. This is one of a series of webinars covering basic form and surface texture metrology concepts relating to our products. In this webinar, we'll be looking briefly at some of the influences on measurement uncertainty and some practical suggestions as to how you might limit their effect. If you have any questions during this presentation, please type them into the question and answer panel that's on your screen. I'll try to answer your questions at the end of the presentation. In this presentation, we're going to look at some of the things that affect the quality of measurement on a typical surface texture or roundness instrument. When talking about the effect on measurement quality, what we're really saying is that these things affect the measurement uncertainty when using these instruments. There are some key areas that we shall look at. I've highlighted three main areas, which are the instrument, the environment, and the measurement procedure. Now, clearly I can't cover everything. What I hope you'll get from this presentation is some pointers to the sort of things that you should be considering when evaluating measurement uncertainty or measurement problems, particularly if you're looking to improve your measurement capability. I'll avoid instrument specifications as much as possible. Instead, we'll be looking at those practical things that affect the measurement but are not directly related to the instrument performance. Before moving into the main body of the presentation, I thought it would be helpful to look at two preliminary slides to get us to a point of common understanding. The first slide will outline some of the influences that affect the measurement. The second slide will highlight the scale of the quantity values that we might be measuring with these instruments. In this slide, I've identified some of the areas of influence on the measurement process so we can see how they interact. Obviously, the instrument will contribute to the uncertainty of measurement. The instrument design will have been arrived at in a way that minimizes the contributions to measurement uncertainty within reasonable economic constraints. The instrument will have an inherent noise level, sometimes referred to as the noise floor, that will be seen even in the best environment. However, as I've implied, there are other influences on the measurement quality. These influences are the responsibility of the end user, or user for short. In the first instance, the end user is responsible for specifying the exact configuration of the instrument. Again, economy will play a part in the decisions made. As an example, instruments are commonly available with different gauge resolutions. They might also be available with different anti-vibration solutions such as solid rubber mounts, pneumatic mounts, or even active anti-vibration mounts. These different configurations will each have their own characteristics. The environment is another area that is the responsibility of the user. Key considerations might be temperature control and vibration, both of which will impact on the measurement uncertainty and both of which are clearly outside of the control of the instrument manufacturer. The measurement process or procedure will also impact on the measurement, as will the parts themselves. Again, these are determined by the user and not the instrument manufacturer. There is at least one more key influence on the measurements, and that is the measurement standards being applied. These could be local, national, or international standards. They'll often have an impact on both instrument design, or the user, or both. The second preliminary topic is measurement scale. This is included to help us come to a common understanding of the units of measurement that we're using by relating them back to things that we might all have encountered in some way. In the field of surface metrology, we deal with a significant range of dimensions, from less than a millimetre to 1,000 millimetres or more. However, most of the characteristics that we deal with are specified in the default unit of micrometers or 1,000th of a millimetre. We happily subdivide the micrometer. For example, we might talk about form deviations that are of the order of 1/10 of a micrometer. With surface texture, we often talk about values that have a smaller scale than this. For example, it's not uncommon for surface roughness RA values in the order of 0.01 micrometer. If the micrometer is the default unit for specifying the quantity values that we're interested in, then just how big is 1 micrometer? The graphic here gives an indication of scale within the range of 0.01 micrometer to 1 millimeter, related to things from everyday life. We're all familiar with the 1 millimeter scale marks on a steel rule or tape measure. Going smaller than that, the thickness of a typical sheet of printer paper is about 100 micrometers. A fingerprint might leave a residue that is between 10 and 50 micrometers, and this is something to remember later when we discuss handling and contamination. Dust particles and bacteria cover a wide range, extending from about 25 micrometers down to as small as 0.25 micrometers. This range also encompasses the range of visible light, which is roughly from 0.7 micrometer down to 0.4 micrometer. One consequence of this is that even if we use a good optical microscope, we probably can't even see the smaller dust particles and bacteria, yet our surface metrology instruments have resolutions far smaller than this scale. Beyond small dust and bacteria particles and the visible light spectrum, we have virus particles with diameters about 0.2 micrometers to 0.2 micrometers. So in this quick look at scale, we've covered 5 orders of magnitude down from the millimeter. Now we could continue to reduce scale, but not much further. In fact, by the time we get below 0.001 micrometer or 1 nanometer, we start to move into the realms of atomic scale. In this next section, we'll look at some of the aspects of the instrument that contribute to the measurement uncertainty. For the purposes of this discussion, systematic errors such as axis straightness are not considered. A typical instrument, such as the one shown here, has several major components. Very clearly, there is a mechanical structure containing the instrument axes and datums, together with some sort of frame that mounts the instrument onto the supporting structure, which in this case is likely to be the measuring room floor. Each of the axes directly involved in the measurement will usually have some method of moving the axis or some form of drive mechanism. The drive mechanism is likely to contain a motor and drivetrain, both of which can add noise into the measurement. The gauge will have a given resolution or resolutions, and of course the electronics might also be considered as a noise source. Each of these systems contribute to the internal noise level of the instrument, which will typically be specified at particular measurement conditions, such as gauge resolution and axis speed. The stylus is worthy of special attention. It's the link between the gauge and the surface under test. It's also a good example where all 3 areas of influence interact. Various features of the stylus, such as the length and size of any recess piece, will be governed by access criteria. 2 different examples are shown here. The upper graphic shows a recessed stylus being used to access a feature that is obscured by another feature on the surface. This might require a longer than normal recess. The lower graphic shows a different design of stylus that is needed to measure inside a small bore. In this instance, the recess depth has been minimized and the stylus beam width narrowed towards the tip. These are examples where user requirements are influencing measurement decisions. At the same time, the stylus tip and stylus force might be dictated by standards. For example, in surface texture measurements, these two parameters are dictated by ISO 3274. Design choices will affect the materials used in the stylus and its overall geometry. One good example is the interface between the stylus and the gauge. Regardless of the geometry of the measuring part of the stylus, this interface will have been decided by the instrument manufacturer to allow for interchangeable styling. All of these factors will impact on the dynamic behavior of the stylus and will therefore impact to some degree on the measurement uncertainty. Whilst the static force might be dictated by standards, the dynamic measurement force is a function of the traverse speed and surface acceleration, as well as the static force. Subject to the speed selections of the instrument, the choice of measurement speed is a user selection. The surface accelerations are dictated by a combination of the traverse speed and the form of the component. This again is a user influence. We often talk about the concept of tracking, the ability of the stylus tip to follow the surface of the component. Another way of looking at this is to consider stylus flight. This is the same concept, but stated in a different way. Stylus flight is where the stylus tip leaves the surface of the component because the forces on the stylus are insufficient to keep the stylus in contact. This might occur where the stylus tip has been forced rapidly up a feature on the surface, such as a machining mark. Once the stylus is in flight, the main force on the stylus is the static stylus force, which will accelerate the tip towards the surface again. The time to reach the surface, and consequently the distance to the next measurable point on the surface, is governed by the trajectory of the tip. Moreover, the tip might well continue to rise off the surface for a brief time after leaving the surface. When the tip contacts the surface again, it might also bounce for a while. The amount of bounce will depend on a variety of factors, including the damping provided by the choice of stylus materials. Stylus flight is very much like a rally car driving over a bump. If the speed is very slow, the vehicle's wheels remain in contact with the road surface at all times. But above a certain speed, the vehicle will leave the road surface. How far the car travels before it hits the road again is determined by gravity and the initial trajectory. Once the vehicle hits the road, it might well bounce, although some of the bouncing will be absorbed by the suspension. There is another concept to consider, which is stylus resonance. The stylus will exhibit some vibrational modes. The frequencies of these vibrational modes are known as the natural frequencies. The lowest of these natural frequencies will tend to limit the maximum frequency that the stylus can usefully detect, as measurements near to this frequency will result in erroneous gauge readings. Remembering that we are actually trying to measure surface wavelengths. For any given surface wavelength, the frequency seen by the stylus is determined by the traverse speed divided by the surface wavelength. When measuring small surface wavelengths, it might therefore be necessary to restrict the measurement speed. This is clearly an area where the instrument design and user influences overlap. Stylus resonance and stylus flight can both be affected by external factors, such as transmitted vibration. In this slide, we can see a representation of how stylus flight might appear when viewing a highly magnified portion of a surface profile. The characteristic form of the flight shows a sequence of parabolic waves whose wavelengths at the mean line decrease with time or distance. Similarly, the amplitude of the waves decrease with time or distance. The first wave after leaving the surface is likely to be highly irregular, as this is largely governed by the stylus trajectory at the time the tip leaves the surface. Stylus flight can be mitigated to a large extent by reducing measurement speed. As mentioned previously, stylus resonance is mainly excited by vibration. This is any vibration reaching the stylus or gauge. Stylus resonance manifests itself as an almost constant frequency, which is dependent principally on the stylus design. The amplitude will be dependent on the driving force or vibration level. The wavelength due to stylus resonance is very short and is typically shorter than common LS filter values. The effect of resonance on the profile may therefore be reduced by the LS filter. Resonance can also be caused by regular surface imperfections, which, when measured at a constant speed, equate to a frequency that is close to the natural frequency of the stylus, or a simple subharmonic. In this situation, it might be necessary to reduce the measurement speed. The discussion on stylus resonance brings us to the next section in this presentation, which is environmental effects. There are two main environmental effects that affect the performance of the instrument: temperature and vibration. Temperature changes during a measurement can cause drift, primarily due to differential expansion. Many of the measurements that we might take might be completed quickly. In such circumstances, the effects of temperature changes within the measurement room might have little effect because of the short timescale. However, some of the measurements that we take might involve a much longer timescale. For example, when measuring on a roundness instrument, it is quite common to take several measurements to establish an axis and then take further measurements using this axis as a datum. Temperature changes during this process can cause drift, affecting the axis definition that we have taken. Where this is an issue, the magnitude of the drift would have to be quantified and taken into the account into the uncertainty budget. Instrument sighting is important. For example, if the instrument is close to a window, direct heating from sunlight might cause significant differential heating of the instrument, which in turn will affect the measurements. The same is true for radiators and other heat sources. Drafts are another issue. Ideally, the instrument should not be sighted in an area of rapid airflow, such as near to an air conditioning duct, opening window, or a door. These effects can be reduced by using an environmental cabinet to shield the instrument and measurement area from drafts. The second major issue is vibration. The two sources of vibration are airborne and floorborne. With airborne vibration, the effects are likely to influence different parts of the instrument, whereas the floorborne vibration, the effects are likely to impact the whole instrument structure. We've already mentioned drafts. Aside from differential cooling or heating, drafts can give rise to a source of airborne vibration. Drafts can easily affect the stylus and can also cause vibration in panels and other parts of the instrument. The use of an environmental cabinet can help reduce some of these effects of drafts. Another source of airborne vibration is sound, especially sharp or percussive sounds, such as might result from something being dropped, slamming nearby. Talking close to the instrument can also cause vibrations in the stylus, as the resonant frequency of the stylus is likely to be within the frequency range of a human voice. Perhaps the most significant source of vibration to be considered is that of floorborne vibration. Any vibration in the floor on which the instrument is mounted will be transmitted into the structure of the instrument. This will result in differential vibration within the system, which will in turn affect the measurements. The impact of vibration is complex. The impact is reduced by good design and by the incorporation of vibration isolation or anti-vibration mechanisms. Where the floor vibration is excessive, then an external anti-vibration platform might well be required. There are many sources of floorborne vibration, some of which are listed here. The impact of floorborne vibration is strongly linked to magnification. If you have ever used a camera with different focal length lenses or a zoom lens, you will know that camera shake becomes more significant as the focal length and therefore the magnification increases. To mitigate the camera shake, improved support such as a tripod might be required and the exposure time could be decreased. Not surprisingly, recommendations for laboratory floor vibration limits are linked to magnification. Originally, the recommendations might well have been linked to the use of standard laboratory instruments, such as an optical microscope. Again, for any given vibration level, as the magnification is increased, the vibration will cause increased blurring of the image. To work at the highest magnifications, which for an optical microscope is about 1000 times, vibration must be very low. In surface metrology instruments, it's not uncommon to see magnifications of approximately 0.01 micrometer per 10 millimeter division. This equates to a magnification of 1 million times, hence the maximum allowable vibration level has to be much lower than when using an optical microscope. At the levels involved in surface metrology, the measurement process is key to obtaining good results. No matter how good the instrument and its environment, a poor measurement process can lead to inconsistent results and therefore to a large measurement uncertainty. Control of the measurement process is almost always in the user domain. In this next section, we shall look at some of the issues that need to be taken into account. One of the first things to consider is the measurement loop. The diagram here shows the same component being measured at two different heights within the measuring volume of the instrument. This could be a very real situation when measuring different features on a long component. For each case, the measurement loop through the base of the instrument, the column, the traverse unit, the stylus, the component and fixture, back to the base, is shown by the blue rectangles. Let us assume that floorborne vibration is introduced into the base. If we consider that some small vibration is set up in the column, then the base will act as a load, and the vibration might affect the column as shown by the dashed red lines. Clearly, the amplitude of the vibration will be greatest nearer to the top of the column. This means that vibration will affect measurements taken nearer to the top of the column to a greater extent than near the bottom of the column. Wherever possible, the measurement should be taken nearer to the bottom of the column. Logically, this impacts on the design choices being made for any work-holding fixtures. Ideally, wherever possible, these should minimize the height by which the component is raised. The number of interfaces should also be minimized, as these will not be infinitely stiff and may magnify vibrations or lead to other instabilities, such as component rocking. It almost goes without saying that for best repeatability between measurements, the same portion of the gauge range should be used. Ideally, this should be within the calibrated portion of the gauge range where possible. Many instruments provide an automatic stop-on contact of the gauge that allows the gauge to be brought into contact with the surface either at the midpoint position or at some other user-defined position within the gauge range. Such a feature can be used to help ensure that the same portion of the gauge range is being used. On some instruments, such as our Talleyrand instruments, it is possible to change the relative angle between the stylus and the gauge body, as shown in the graphic. It should be remembered that this shortens the effective stylus length, and this will affect the magnification in the measurement. The effect might be more significant if accurate correction is being used. The stylus should be recalibrated after any such move. Ideally, use a single displacement for the stylus offset and set this prior to calibrating. There are some other points that should be considered in relation to the gauge. Above all, the key is to avoid handling the gauge as far as possible. Where gauge force or stylus orientation is achieved by manual means, these adjustments should be kept to a minimum to avoid heating the gauge, which is likely to be sensitive to temperature in some way. The gauge, by its very nature, is an extremely sensitive piece of equipment, and ideally the gauge should be allowed to settle after any adjustment of stylus angle or gauge force. We've spoken a lot about thermal effects influencing the instrument. However, the same is true of the part being tested. For accurate form measurements, for example, the component should be allowed to stabilize to the temperature of the measurement room and the measurement equipment. Again, handling can cause heating of the component and can also lead to contamination by grease and fingerprints. Contamination is an obvious impediment to obtaining good measurements. Dust particles often show up as spikes in measurements. These particles can be dragged along the surface by the stylus, leading to erratic measurements, or might even stick to the stylus tip. Some of the common stylus tip materials are insulators and can easily become statically charged, attracting and holding particles that will cause problems later. Grease films are another problem. The films can be unpredictable. Repeated measurements might show a form error that appears to be reducing with successive measurements as the stylus cuts through the film. Unfortunately, the grease will often transfer to the stylus tip, causing erratic results or helping to retain particulates on the surface of the stylus. The stylus tip should always be inspected and cleaned as necessary prior to a high precision measurement being taken. Use of a suitable magnifying glass or pocket microscope would help with inspection. With care, the stylus tip can be cleaned using a jeweler's cleaning compound or a similar process. Good fixturing is essential for high accuracy measurements and for improving the repeatability of measurements between samples. In the case of large components, gravity might be sufficient to hold the component in place. Use of a kinematic mounting procedure as simple as placing the component on 3 slips of paper might be all that is needed to provide a stable measurement. In other situations, particularly with smaller components, the components might need to be restrained using a collet chuck, vise, or other fixture. Wherever mechanical means are used to constrain a component, care should be taken to limit the forces applied to the component so as to minimize distortion effects due to compression. In this presentation, we've looked at some of the key influences affecting high-precision surface metrology. We've seen how these influences are divided between the measuring instrument design, the end-user requirements and choices, and measurement standards. In particular, we've looked at some issues relating to the instrument and its use, environmental effects, and the effect of the measurement process. I hope you found this presentation to be interesting and informative. You can find more presentations on various topics relating to our metrology products on our website at the address shown on the screen. Thank you for your time, and I hope you'll be able to join us in the future for more of our webinars. Are there any questions, please?
Hello, Dr. Mike, and thank you very much for a very interesting presentation. I'm just checking to see if we have any questions. There's one question come in, which is, can you make any recommendations for stylus tip cleaning? You mentioned about stylus tip contamination.
Yes, the recommendation that I would make is to use a Stylus cleaning compound, which is something that you can find on a store that would be providing things for jewelers to use for cleaning watch components and other small components such as that. There are a few of them around, so if you do a search on the internet, I'm sure you'll find some.
Thank you very much. That's the only question we have today, but just to say on behalf of everybody listening, thank you very much for your time in preparing this and for sharing this presentation today. So thank you, Mike.
Thank you.
Okay, we're going to end the webinar now and say goodbye.